Okay, ladies and gentlemen, this is going to be our matter and energy review video in which I go over the content. If you're looking for any review with the practice test, that will come in another video coming later. Alright, so these are the list of topics I'm going to go over. I also added towards the end physical and chemical properties. And so we're going to start with what is matter. And it's anything that has mass, takes up space, and sometimes you could even call it stuff. And so there are two types of matter that you guys learned about: pure substances and mixtures. Now, pure substances can be broken down into elements and compounds, whereas mixtures have two types: homogeneous and heterogeneous. Okay, so pure substances have definite and fixed composition, and they also share the same unit sets of properties. Elements we've learned previously are pretty much the purest form of matter in its most simplified state, whereas compounds, they are combinations of elements, chemically combined elements. Now notice here I've listed some examples. If you see one of the same type of element, then it's just an element. Even O2 and H2, these are diatomics. So you might see them represented by these diagrams. So while you have two circles representing an element, there's two of the same kind, so therefore it's an element. Whereas here, compounds are comprised of a mixture of elements. So you need to see different types of circles to show that it's a compound. Example, H2O could be like this. NaCl could be like this. NH3. So two different types of elements have to be, at least two different types of elements have to be compounds. All right, mixtures. These are physical combinations of two or more substances, could be elements or compounds. So they have to be different types. They can also be physically separated into components. So here I want to highlight that mixtures do not equal compounds. This one here is physical. This one here is chemical. So in order to break down or combine elements to make compounds, you must undergo a chemical change, a chemical reaction. Whereas mixtures, you can physically do it yourself. Okay, and here composition can vary from one sample to another. On the other hand, compounds, they have to have the same composition, different samples. Whereas here, mixtures, different composition, different samples. Okay, now let's look at the two different types of mixtures: homogeneous and heterogeneous. So homogeneous, let's start with, is even mixing. Examples could be solutions. So if you mix an element with water to make a solution, that's homogeneous. So you could submerge NaCl in water. So typically this symbol, AQ, aqueous, indicates that's a solution, therefore it's homogeneous solution. On the other hand, heterogeneous is uneven mixing. That means if you take a sample, it's not going to be the same composition throughout. Whereas homogeneous, take a sample, it's the same amount throughout. It's even. So heterogeneous mixtures could include soil, as an example. Take a clump of soil, you might not have the same composition of material in that soil. Now what I'm going to draw here in this corner is what a particle diagram would look like for a mixture. And so you're just going to have a mixture of different elements, different compounds. Etc. Could be like this. It's a mixture of different things. Now, before I talked about being able to physically separate mixtures, and these are the methods you use to separate mixtures. And it depends on homogeneous versus heterogeneous solutions. Now, distillation is the same as boiling substances. It utilizes boiling points. So for example, if you want to separate salt from the water, then you got to boil it to separate the salt from the water. It uses the boiling point of water. It boils the water, lets it evaporate, and all you're left with is the salt. So example could be salt, water. All right, now let's talk about chromatography. So this is where mixtures are allowed to separate into layers. It could either be done in paper chromatography or gas chromatography, and you're going to see the different components of the mixture separate through this method. Now, heterogeneous mixtures can be separated by either decantation or filtration. So decantation is the same as pouring. So for an example of that, this is how you could separate oil and water. So those two materials don't mix well, oil and water, but you could separate the two. If they do a little bit of mixing, and you could separate them through decantation. Now filtration, if you think back to the lab, is where you use a whole filter. And I'll draw this whole setup here. And you have this cone sort of thing to filter out, in which you had the filter paper, you had a mixture of sand and salt water, and you got to separate the sand from the salt water. And so here, bigger molecules get trapped in filter, whereas the smaller ones pass through. So if you think back to the lab, the sand got stuck in the filter paper because it was the bigger molecule, whereas the salt water, being smaller, seeped through and landed in this beaker, like that. All right, solids, liquids, and gases. These are the three states or phases of matter. And if you see those symbols, S, L, and G, next to a certain symbol in a chemical formula, then that indicates the state of matter it's in. So solid, liquid, and gas. Okay, so here I sort of drew out a table. And here I'm asking if they have definite volume or definite shape. Solids do have a definite volume. Liquids definitely do as well, but gases don't. Now for shape. Solids do have definite shapes, whereas liquids, they don't. Instead, they take shape of the container. Think about liquid water. It could take the shape of a water bottle, or it could take the shape of a glass, depending on the type of volume that's containing it. Now for gases, they also don't have a definite shape. Very random. I also want to add that solids have high stability. As a result, because they're very stable, they have low potential energy. Liquids is sort of in the middle, whereas gases, they have very low stability because it's so random. The particles move in however they want. And so as a result, they have high potential energy. Okay, so I'm going to draw diagrams for each of these phases. So solids are very rigid. They form, most likely to form crystals. So it's the same pattern throughout. Okay, whereas liquids, they're kind of smoother, kind of bend a little bit. A looser pattern on the other hand, whereas as opposed to the solids. Now gases is any random order, so they could be all over the place without any sort of given pattern. All right, endothermic versus exothermic. These describe different processes, whether it's absorbing or releasing heat. Endothermic here, endo means to absorb heat, versus exothermic is to release heat. Think about exhaling. You're releasing air. Now, how would this look like in terms of reaction? So in terms of a chemical equation, you would probably see heat as a reactant. Heat as reactant. Whereas in exothermic, heat as a product. So what does this look like? So let's say here, you want to break down X and Y. Whereas here, on the other hand, you're going to see heat on the right side. So releasing is on the right side, absorbing is on the left side. Okay, so now we're up to the phase changes, and there's 6 types you're responsible to know. Fusion is this also called melting, and this is from solid to liquid. Next we have freezing, oopsies, which on the other hand is the opposite direction. That's from liquid to solid. All right, evaporation is this time it's from liquid to gas, whereas condensation is from gas to liquid. Evaporation, on the other hand, can also be called boiling. Deposition and sublimation are 2 very special kinds, where deposition goes from gas to solid. It totally bypasses the liquid stage. And sublimation is on the reverse, solid to gas. Now, each of these processes can be categorized as either exothermic or endothermic. So, going from solid to liquid, you absorb heat, so that's endothermic. So you need to raise the temperature to get to that. Freezing is exothermic. Evaporation is endo. Condensation is exo. Deposition is exo. And sublimation is endothermic. Okay, now let's put it all together. So solid to liquid, once again, we call that melting or fusion. On the other hand, liquid to solid is freezing. Liquid to gas is evaporation. Gas to liquid is condensation. So notice going from right to left, we're going in the endothermic direction. So you need to absorb heat to go from solid, liquid to gas, and on the other hand, you're releasing heat going from gas to liquid to solid. So over here, solid to gas, increasing potential energy. over here, decreasing potential energy. And let's add a bit about stability. So more potential energy means low stability. It's more random. All right, now let's talk about temperature and heat. So temperature here is not a measure of heat. It's the measure of average kinetic energy. Which is all about here, the movement of particles. Heat, on the other hand, is a type of energy also transfers from high temperature to low temperature. It always moves from high to low. Okay, now going back to temperature, I want to add that there are two types of units. There's Kelvin and degrees Celsius. For us in America, we measure temperature by degrees Fahrenheit, but it kind of converts to degrees Celsius. Degrees Celsius is often used for science, as is Kelvin. Degrees Celsius you might also see in other countries around the world, just because it's easier and more standardized. Now there are two types of temperatures you need to remember. Okay. So 0 degrees Celsius is the freezing point or melting point of water. And 100 degrees Celsius, that's the boiling point of water. Okay. In Kelvin, there's such a thing as absolute zero, where it's the coldest temperature ever, in which all particles don't move at all. And the difference between Kelvin and Celsius can be expressed in this relationship right here. So I'm going to divide this part here. And let's pick this color. So the difference between Kelvin and Celsius, you can invert it. It's in the reference table. And so you take your temperature in degrees Celsius and you add 273. So let's say you start at 100 degrees Celsius and you wanted to convert it to Kelvin. So 100 plus 273 gets you 373 Kelvin. Okay. Now for later on, both of these temperatures are interchangeable because a lot of the operations we'll do is just adding and subtracting. Okay, that's a note for later. So as an example of heat going from high temperature to low temperature, let's take an object here. Let's say we have ice cubes. This was in the practice test. Let's say the water had a temperature of 20 degrees Celsius and the ice cubes are 0 degrees Celsius. So heat is then going to transfer from high to low. It's going to go from the water into the heat. Water into the ice. That's what I meant. Now there are two types of curves that show the relationship between temperature and time in the phases of a substance, and that's heating curve and cooling curve. First, we're going to talk about a heating curve. And so it shows that over time, the temperature is going to increase, heating up, going from a solid to a gas, solid, liquid, gas. Now, I want you to take note here. You see these plateaus? That's where you see a constant temperature and a phase change. So, flat slope equals phase change. Whereas over here, these inclines equals increasing temperature, but also a single phase. It's only during the phase change in the flat slopes where you see a substance in between the two phases, and that's while it's in the midst of changing phases. Okay. Also on another note here, I'll put another color. As you're increasing temperature, you're also increasing the potential energy going from solid liquid to gas. Okay. Now also remember, temperature is the same as kinetic energy. So kinetic energy increases as you increase the temperature, but kinetic energy stays constant during a phase change. Okay. Well, only potential energy changes during these parts. So while a substance is changing phases, it's also increasing its potential energy here. Now before I forget, we also got to name these phase changes. So going from solid to a liquid, that is going to be called fusion or melting. And over here, liquid to gas, that we call as evaporation. Now when they ask for the boiling point, that's when it starts to evaporate. So here's the boiling point temperature. And the melting point is right here. And also one last final thing about heating curves. This here shows endothermic processes. So think about it, you're absorbing heat to heat up. Now here we have a cooling curve. It's the acts in the opposite direction. All right, so same thing applies during the flat slopes. So this time we see decreasing potential energy and still a phase change. Same thing here, decreasing potential energy, phase change. Now over here, during this phase changes, that we call our condensation point, or sometimes they keep it simple, boiling point, and over here is our freezing point, where it goes from liquid to solid. So like I said before, this gas to liquid is condensation. And over here, liquid to solid is freezing. And to top this off, cooling curves are exothermic. So think about it, you're releasing heat to cool down. All right, now there are three equations we use for heat calculations. And here, Q equals mc delta T. Sometimes I like to call it MCAT. Now you might see delta T expanded into T2 minus T1. Always follow that, where T2 is your final and T1 is your initial temperature. So final minus initial. The next equation you use is Q is equal to MHF, heat of fusion. And then the last one is Q is equal to MHV. Now, when do we use these equations? First of all, let's figure out what do these variables mean. So Q is equal to heat energy, measured in joules. So joules or calories is the unit for heat energy. M is the mass of the substance. C is the specific heat capacity. So our unit for mass is grams, and our unit for specific heat capacity is joules per grams degrees Celsius, or degrees Kelvin. So it's telling us how many joules of heat do you need to increase 1 gram of a substance by 1 degree Celsius. Okay, T is temperature. HF is heat of fusion. and HV is heat of vaporization. So both of these have units of joules per gram. Which tells us how many joules of energy do you need to convert at least 1 gram of this substance to the next phase. So let's figure out our reasons for using these equations. So Q equals mc delta T you use for temperature changes. When you're changing the temperature of a substance, you need to figure out how much energy you need for that. Q equals mHF, heat of fusion, when changing between solid and liquid. So while you're melting or freezing, you're going to use that equation. And then this one, heat of vaporization, when changing between liquid and gas. Could be one or the other. All right, now there are 3 constants here, and I'm going to asterisk them. These are specific numbers that don't change, but they're characteristic of certain substances. So if you look in your reference table, I think it's reference table B, they list the constants for water. So only for water. So if the problem specifies water, then you're going to use these numbers. If they don't specify water, they say something else, then that's when you're either going to solve it or they give it to you in the problem. So these are the constants for water. So C is equal to 4.18. HF is 334. And HV is 2,260. Okay. So in problems like this, when they ask for the heat, you look for Q. If they ask for the mass, you look for M. If they're looking for final temperature, make sure you calculate for delta T first, and then you add it on to T1. Or I'd rather you expand it to T2 minus T1 instead. So instead, I'll write that for you guys. Now this equation, you could expand this into Q equals MC T2 minus T1. You could do it like that. All right. Now we're finally up to our last topic here, physical versus chemical properties. So physical properties, this we just covered recently, is that you can observe or measure the properties of a substance without changing the chemical composition. And there are 2 types, extensive and intensive. Extensive here depends on sample size. Examples include mass, weight, volume. So imagine you're taking a fistful of soil as well as a tiny little finger bit of soil in the other hand. So different sample sizes, you're obviously going to have different masses, different weights, and different volumes of that same substance. On the other hand, intensive properties do not depend on sample size. So taking that same analogy, fistful and a finger bit of soil in 2 opposing hands, they're still going to have the same type of properties, including melting point, freezing point, and what's the other one? Boiling point. So they're still going to have that. They're also going to have the same solubility, which is the ability to dissolve. You could also talk about color, odor, etc. Chemical properties, on the other hand, can be observed or measured through interactions with other substances. So often the case with chemical reactions. So, for example, burning, combusting, decomposing, reacting, or rust. That's an example of a chemical property. Magnetism, if you think about the element iron, it's a type of substance, type of element with certain properties that allow it to be attracted to magnets. Iron could also rust, so that's another example of a chemical property of iron that's characteristic of that specific substance. All right, so now we've finally come across physical versus chemical changes. This is how you're going to change substances. So physical changes is a change of form without changing chemical composition. So no chemical reactions. Examples include phase changes. Think about water to ice. Still the same H2O, still the same chemical composition, but you're physically changing what it looks like, going from liquid water to solid ice. You could also talk about size change. You could cut up ice, still the same substance, just different portions. And also dissolving. You could dissolve salt into water, still salt, but it will start to break down into its two ions. Now, chemical changes, on the other hand, is changing the composition, its identity and properties from one substance to another. And typically, the most common way to do this is by chemical reactions. You could form compounds this way. That's a chemical change, or breaking compounds. You can only do that by chemical reactions. So that's a chemical change, because you're changing the actual property, the actual composition of an element or compound. All right. So that's it for this matter and energy review. Later on, I'll put up the practice test review video in a bit. Okay, so good night.